Johnston Island portion of the 1962 Dominic test series conducted by Joint Task Force 8 included two types of tests. One involved a number of high-altitude nuclear detonations carried aloft by various missiles launched from the island for a study of the effects produced by such detonations. And the other was a group of 5 airdrops over the ocean clear of the island, but within the Johnston Island danger area. These airdrops were a continuation of certain advanced concepts investigations started during the Christmas Island operation.
The high-altitude series had these basic objectives. First, there was an evaluation of the missile kill mechanisms produced by high-altitude detonations. Secondly, an investigation of the effects of such detonations on our electromagnetic surveillance and tracking capabilities and on the maintenance of long-range communication systems. Third, the acquisition of further data on the basic characteristics of such detonations and the physical basis of these effects. And lastly, an evaluation of high-altitude diagnostic techniques and detection systems. As you can see, these are related quite closely to both the offensive and defensive aspects of the problem. We did not go into the operation uninformed in these matters, but designed our experiments on the basis of data gathered from prior high-altitude tests. The teak and orange events during Operation Hardtack in 1958 provided our first basic data on nuclear effects at altitude. The 3 Argus detonations in the same year gave us additional information on these effects. But the shots had raised perhaps more questions than they answered, and these questions could be resolved only by additional tests. The purpose of this program was to provide points of departure for still further determinations.
The Starfish, Bluegill, and Kingfish tests were launched by modified Thor missiles, which initially were the only planned high-altitude vehicles. The missile carried externally mounted instrumentation pods for each event to collect data on blast overpressures and thermal and nuclear radiation as potential ICBM kill mechanisms. The pods were programmed to separate from the missile in flight so as to be at specified points in space near the detonation and properly oriented to acquire the desired data. After each event, helicopter and ship teams recovered the now highly radioactive pods from the sea for delivery to the island and subsequent analysis of their data. In addition, a variety of auxiliary rockets, also launched from Johnston Island, were used to position other instrumentation which telemetered data on X-ray and beta ray pulses, data on radio frequency attenuation through the fireball, explosion debris, and a number of other technical functions. These rockets were fired at carefully programmed times on trajectories oriented around the detonation point and tracked and plotted in space for later analysis of their data. In addition to tracking and recording stations on the island, there were a number of similar stations aboard instrumentation ships underway in the area. These mobile stations could be shifted to positions adjusted to the special requirements of each shot. At the same time, there was an array of airborne instrumentation platforms, both in the vicinity of the island and in the southern conjugate area, to document and record data from vantage points above the clouds. P-2V aircraft, together with destroyers, provided the security and safety surveillance of the extensive danger area surrounding the theater of operations. There were many other sites at remote locations throughout the Pacific Ocean basin, designed, constructed, and oriented to observe and record the phenomena associated with each test. These were located at such widespread geographical locations as the Hawaiian Islands, New Zealand, Fairbanks, Okinawa, Rarotonga, Trinidad, French Frigate Shoals, Kwajalein, Tonga, the Aleutians, Wake, Palo Alto, Fiji, Midway, Palmyra, Christmas, Canton, and American Samoa. This particular site at Tutuila in American Samoa is representative of the many set up to record test data from the Southern Magnetic Conjugate area. The station was established here to observe and record such things as debris distribution, magnetic and electric field measurements, cosmic noise absorption, optical measurements of the burst and of the fluorescence created by beta rays and bomb debris, plus extensive photographic coverage of the size, intensity, and motion of the conjugate point auroral phenomena. This, basically, is a capsulized breakdown of the instrumentation designed for the collection of the great mass of data required from the high-altitude phase of Operation Dominic. One of the key sites for the entire series was a ship at the pier at Johnston Island. In this ship, the range tracker, with a range safety tracking and control system so vital to the safe and accurate conduct of all firings during the high-altitude phase. The first of the Johnston Island high-altitude firings was bluegill. Ignition of the propulsion system appeared normal. And liftoff was as programmed. The range safety tracking radar lost track, and it was necessary to destroy both missile and the warhead after a long flight on what was later analyzed to have been the correct trajectory. This was most disappointing with respect to the event, but it did show the effectiveness of the destruct system, and it led to a number of important strengthenings of the overall range safety tracking system. The next attempted high-altitude shot was Starfish on the 19th of June. It, too, was unsuccessful. This failure was a direct result of special test modifications which had been made to the missile. Aerodynamic eddies caused by fixtures on the missile exterior were confirmed to have drawn exhaust flames up the outside of the missile skin, causing overheating and failure of key structural members. As a result, the missile broke up in flight. Rather extensive modifications were made on the missile to eliminate the possibility of recurrence. On the 8th of July, Starfish Prime, the second try at Starfish, was launched and was entirely successful. The warhead detonated at an altitude of 400 kilometers, 31 kilometers south of Johnston Island. This is how it appeared in still pictures from Maui Island in the Hawaiian chain. But this was not to be the end of the missile problems on the operation. On 25 July, the Thor vehicle for Bluegill Prime had a one-of-a-kind casualty, diagnosed as a sticking fuel valve, which caused a fire at motor ignition. Both missile and warhead burned on the launching pad. Damage to the pad was extensive, as could be plainly seen next morning. Less visible, but more dangerous, was the long-life radioactive contamination of the pad area from the warhead. It was obvious that this would cause a significant delay in the operation. Work began immediately both on the repair of the original pad and on the installation of a second one for a backup against this sort of lengthy delay. It was during the same period of rebuilding that two events were added to the high-altitude program. The tentatively scheduled Kingfish event was also authorized for execution at this time. By mid-September, work had progressed to a point from which operations could resume. The tempo increased as units which had gone home or had otherwise been shifted during the rebuilding phase returned to their stations to take up their duties where they left off. But again, our troubles were not over. On 15 October 1962, we had one more failure when the 4 missile carrying the bluegill double prime device experienced electrical shorting in the engine actuator circuit at 85.8 seconds after liftoff, with a resultant loss of attitude control. The remaining 4 events, Checkmate, Bluegill Triple Prime, Kingfish, and Tightrope, were all successful. A tremendous amount of data was recorded during these events. Literally amazing success was achieved in the complex positioning of instrumentation, including air and rocket-borne equipment, and in the recovery of the recorded information. Some of this information will require a long time for final refinement and analysis. But at the present state of that analysis, it is clear that this further work of refinement will not greatly modify what we now know from these tests, which permits us to make the following statements. Unfortunately, measurements of missile kill mechanisms of nuclear detonations at altitude, one of the most important objectives, was least successful. As to radar surveillance and tracking systems, nuclear detonations do cause temporary loss of radar tracked targets when the fireball intercepts or is close to the radar target line. The significance of this depends partly on the size of the fireball, how long it lasts, and its position relative to the radars concerned. This could be vitally important in actual war operations because of the relatively enormous fireball sizes at altitude and their persistence for times which are long relative to the times involved in possible missile attack. We do need more information on this fireball blackout. As to communications blackouts, these proved to be not as severe in these particular tests as had been anticipated. Some operationally important frequencies did suffer interferences. Although this interference was temporary, the time involved could be critical in certain wartime situations. The effects of high-altitude detonations on communications were found to be most complex in nature, and more information is needed before the phenomena are fully understood. Finally, a large amount of phenomenological data was collected on high-altitude effects in general. Analysis of this data is providing us with an improved understanding of such effects. It is also clear at this point in that analysis that there remain gaps in our experimental data which can only be closed by further tests.
In addition to the airdrops themselves, there was another aspect to the operation of special interest. This was diagnostic measurement by an airborne instrument array instead of the usual primary reliance upon ground-based instrumentation.
The scheme for using an airborne test instrumentation array had been used during the Christmas Island series in a trial and backup role. There were some initial disappointments, but as the series progressed, its effectiveness steadily improved. By the end of that operation, the program had advanced to a point which justified going ahead with the added airdrop events at Johnston with the air array as the primary and only available method of obtaining much of the needed data. The plan provided for an airborne package made up of the B-52 drop aircraft, C-130 and KC-135s carrying special instrumentation and camera setups for diagnostic studies, The RC-121s for primary and secondary control of the air array, C-118 effects aircraft for the conduct of chorioretinal burn experiments, the B-57D sampler controller, airborne to direct the sampling missions, and the B-57 samplers for cloud penetration missions to obtain samples for the laboratories. The entire array was under the control of the Air Task Group Commander in one of the RC-121s. Surface support for the air array consisted of destroyers patrolling in the danger area to ensure that no unauthorized ships were within the restricted zone. Target rafts anchored at designated points in the open ocean to provide a focal point for assembly of the airdrop array. And Johnston Island as the advanced base for P-2V surveillance aircraft and for recovery of the sampler controllers and the radioactive samplers. On the carrier Princeton, underway in the drop area, overall control was maintained by the task force commander in flag plot. These were the devices tested.